Okay, this is part 4 of the May 2024 Unit 4 IAL Edexcel Physics exam on further mechanics, field theory and particle physics. This question is on particle physics, so it comes at the end of the course. So I'm going to just do this one question and I'm going to try and keep the videos short and you can keep going back for more. Don't forget to like, share and subscribe. So there's 3 parts already that we've done. Make sure you go back and watch them if you haven't done so already. And share them with your friends, please. My aim is to get 1,000 subscribers as soon as possible before the end of the academic year, and we really appreciate your support in helping us to get that. According to the standard model, or the standard quark lepton model, I should say, most of the visible matter in the universe consists of quarks and leptons. The table shows 6 types of quarks and their charges. Okay, so the charge, the up, charm and top, yes, if you like, CUT, are above the rest in that their charge is the positive one. Okay, so the up is the normal quark and the charm is the second generation of the plus 2/3 Coulomb quark, and the top was discovered in the late 90s and was third generation of the positive quark. The other 3 quarks, down, strange and bottom, and if you remember cut above the rest, then the others will be the minus charge, the same as a down quark. Okay, now 99.999% of the matter will be made of up and down quarks. Okay, state the quark structure of baryons and mesons. So this is a nice 2 marker. Baryons are made of 3 quarks, a bit like protons and neutrons, and a meson is an unstable combination of a quark and an antiquark. Yes? So those are the 2 types of heavy particles. Anything made of quarks is called a heavy particle, and together this family are called hadrons. Okay? It then says scientists have proposed the existence of particles called leptoquarks. I'm not so sure about that. Leptoquarks have both baryon number and lepton number and decay into a quark and a lepton. The fact that they're saying they decay into a quark and lepton means that a leptoquark, if it could exist for a short amount of time, it would only be able to exist for a very, very small amount of time because it's not going to be stable. The reason there are particles made of quarks like these and particles made of leptons is because they don't really go together. Okay, one type of leptoquark has a charge of plus 5/3. Well, remember that the quarks have a charge of plus 2/3 if they're positive. Yeah, that means it's plus 2/3 plus another 1 electron charge. So it must be plus 2/3 plus another 3/3 if you like. That means if the quark is responsible for the plus 2/3, that means the lepto part of the leptoquark must be responsible for the plus 1 charge. That gives you a clue. It says determine the baryon number and the lepton number for this theoretical particle called leptoquark. Include the suggested quark and lepton in your working. All right, so this is about conservation laws in particle interactions, if you like. So, first of all, the charge. So the charge is Q. So we've already done that. Plus 2/3 must be from the quark. So it could be a C, a U, or a T in theory, yeah, as shown in the table. And it must be, because it's a plus 1, now leptons are normally minus 1 like an electron. Okay, so it must be an antilepton. It must be an antilepton. That means it could be a positron, a positive muon, or a positive tauon. So plus 1 indicates that it must be an anti-lepton, okay, for the charge to be conserved. You start off with 5/3 of a charge, and you end up where it splits into plus 2/3 and plus 1, okay? So, the quark, we've done the quark composition. Then, it says determine the baryon number, so I've done that as a B, the baryon number, must be plus third. Now, normally, we don't do the baryon number of a particle like this, which is a theoretical particle, would not be made of one quark. In fact, you don't have one quark particles, okay? Because, remember, it says it would decay into a quark and a lepton. Now, quarks have never been discovered to exist on their own, so this is just a theoretical situation. If it did exist, then its baryon number would be incomplete. Yes, it's normally plus 1 or minus 1. This one, the baryon number would be a third, a fraction of a positive baryon. And the lepton number must be minus 1 because we know it's an anti-lepton. And leptons are plus 1, anti-leptons have a lepton number which is negative. Okay, so minus 1 lepton number means an anti-lepton. Baryon number minus 1 would be an anti-baryon. Okay? Hope that makes sense. Scientists then, for part 2, scientists search for new particles using high energy particle collisions. That's what particle accelerators are for. The highest energy particle collisions involving the highest energy particle collisions involve colliding protons moving in opposite directions, okay? Each with energy of 6,800 gigaelectron volts. That means you've got to multiply that by 2. Now, at first in my answer I'd written this was 10 to the 12, but yeah, to correct that's giga is 10 to the 9, yeah? So originally I'd written 10 to 12 by mistake because 6,800 times 10 to the 9 would be 6.8 times 10 to the 12. Okay, so just an error. It is estimated, it says here, that that 11% of the total energy of a collision, yeah, could be converted to mass of a new particle. So in other words, every time you have a collision, if 11% of the collision energy goes into making mass, you could work out something mathematically along those lines. Show that the maximum mass of a particle that can be produced is therefore about 3 times 10 to the minus 24 kilograms. So again, this is theoretical. If 11% of the two colliding beams, yeah, which is 6,800 gigaelectron volts each, times 2 of them, yes, so you put that in, that's the energy available in gigaelectron volts, and you want 11% of it, and you want it in joules. So to multiply from electron volts to get them into joules, you always multiply by the charge of these particles, which in this case a proton, so it's 1.6 times 10 to the minus 19. Remember, the energy in joules is equal to the charge times the voltage. In this case, we're talking about 6,800 gigavolts, yes? And charge is Q. All right, so when you do that, 11% of that energy will be 2.39 times 10 to the minus 7 joules. Now, that's a very small energy for everyday things, but for subatomic particles, you can then work out how much mass it would create if all of this 11% got converted into kilograms. Yeah? So it manifests itself as mass. So you divide this energy by c squared to get the mass, because we want to make m the subject of the equation here. So we've done that, and you'll see that that's 10 to the minus 24 kilograms. So that's about 1,000 times more massive than a proton or a neutron. So that is approximately, to one significant figures, it's closest to 3 times 10 to the minus 24 kilograms. So that's quite massive it's like 1,000 times the mass of a proton. Okay? So it says then, the final part of this question, leptoquarks have not yet been observed. Well, I wonder why. Yes? Suggest why they have not yet been observed. Any reasonable suggestion can score this mark from the mark scheme. Yes? So, the mass is too high, basically. The energy required to produce such a mass would be also very high. Yeah? Now, the mark scheme allows you to put leptoquarks would have leptoquarks would have a mass greater than what we just calculated. Yeah? Because obviously they're saying this is the 11% of the energy. So say they would, mass is too high, energy needed would therefore be too high. So I think that's basically it. The energy of the collisions would be insufficient to create that amount of energy, that amount of mass. Okay? Now, I don't know how they know what the mass of the leptoquark would be. Yes? Did they give us any indication as to that before? No. But basically, the more unstable something is, the more massive it will be. Yeah? So mass is created out of energy according to Einstein's equation. So that's the end of question 14, 11-mark question on particle physics. So that's a good one to use for revision. Yeah. Question 15 is going to go into conservation of energy. So let's do that because we just did conservation laws in particle physics. Let's see if we can get another question done for you now. Okay, question 15. An air table, like those games you play, has a surface with many small holes where air is blown through the holes to reduce the friction. Plastic pucks can then move freely over the table on a cushion of air. Now, if you remember starting Unit 4, it started with momentum, kinetic energy, collisions, further mechanics, basically. The photograph shows the surface of the air table with two pucks on it. You can see what a puck is. So if English isn't your first language, use the diagrams to understand what each word means. Okay? Some students use the air table to investigate the conservation of momentum. Explain how using the air table ensured the momentum was conserved in collisions. Okay? So what would you say? Well, the air table ensures there's negligible friction or very low friction. So pucks can be treated as being in a closed system where no external forces act on the pucks. In other words, we can assume the friction can be ignored. Okay? So this will allow you to say, to observe the momentum before and after as a good representation of conservation of momentum. If there was too much friction, they'd slow down too quickly for you to analyze them. Then it says, part B, the students observed several collisions, between two identical pucks, A and B. One puck was stationary before each collision. And you can see it's going to hit it at a glancing blow, which deflects B downwards, and A then deflects upwards. The angles are given here as A and B. It's not to scale, so you can't measure it, with a protractor. Note that they notice that after each collision, the two pucks seem to follow paths at 90 degrees to each other. Okay, the diagram shows one of the collisions. Okay, so the students recorded the following data for this collision. So the initial momentum of A was the initial momentum completely because B wasn't moving. Yes, that's the initial momentum. Angle A upwards here after the collision was 33 degrees. That means angle B will be about 57 degrees if we use the 90 degrees as the assumption that they're given, that what they noticed in the question. They noticed that after each collision, the two pucks seem to follow paths at 90 degrees to each other's paths. And the final momentum of A was 0.039 kilogram meters per second. Okay, so you can see the difference between the two momenta. Okay, but remember, momenta are also vector quantities. So let's see what they want us to do. Deduce whether the angle between the paths of the pucks after the collision was 90 degrees. So we can't assume it was. They want us to work out whether it was 90 degrees or not. So you've got to work it out. You should use the principle of conservation of momentum, obviously. So for the y components, yeah, that's up and down. The momentum before would be 0 because it was moving horizontally, or in the x component. So in the y component, it will be the a sine, the momentum of a times the sine of a, and momentum of b times the sine of b. They will add up to 0. Yeah? So you could count down as negative, up as positive, for example. So I've written here in a messy way, 0.03 something. I have to go back and look. That's from the table, presumably. So I'm looking what I've written here. So if we go back, it was afterwards, yeah, 0.039. This is what I wrote. 0.039 times sine of 33, because the angle was given to us. And then we can work out that the momentum of B in the opposite direction in the y component would be calculated as the negative value of that. Okay, and then the x component, you do the same, but this time there was an initial momentum, which is given to us in the table, 0.046. This time we know how much the A keeps, yeah, and it's going to be cos of A this time, because we knew the momentum at an angle. So you want to know how much of it is in the x direction, which will be the cosine of the angle between the momentum and the horizontal or the x component. And likewise, you add that together and you should be able to determine it. So these are both basically in the forward direction, okay? So the initial direction that the momentum came in. So once you do that, you now have two simultaneous equations with unknowns in them, okay? The y component of B after must be this, which I've told you before, which if you calculate that, yeah, that's the bit we want to do from here, we come to a value of 0.0212 kilograms meters per second, and that's downwards, yeah, or down the page, yeah, the negative y component, if you like. And then x component of B afterward will be this minus the known component of momentum A. So we now know that's going to be equal to 0.0133. This is to the right. So we know that it moves to the right and downwards, yeah? So the resultant of that would be the momentum of B. Now also this angle theta is going to be the B angle, yeah? So you can also do some trigonometry, opposite over adjacent, 0.0212, which is the downward distance over the distance to the, or the momentum to the right, I should say. That ratio gives you a tan theta of 1.59, so it gives you a value of 57.9, which if you add it to the 33 for A, this would be the angle B that we were working out. It comes to just less than 1 degree over 90, so that's approximately 90 degrees if we're doing it to one significant figure. Yeah, it's actually 91 degrees. But that's good enough for this kind of calculation. Hope that makes sense. And the final part of the question is deduce whether the collision was elastic. Well, if the collision was elastic, then the kinetic energy before must be equal to the kinetic energy afterwards. So does the kinetic energy equal before and after this to the same value? The kinetic energy before is just due to A, and a quick way of doing it is because since we know the momentum in the table, you can change that to p squared over 2m. Yes, if you haven't done that, make sure you know this shortcut equation. We know the momentum from the table, divided by 2 times the mass. The mass is given to us. yeah, here. And then you can work out the momentum before. So we know the momentum before. Now you do momentum after, but the momentum after is split into A and B. Yeah, so you do the same equations twice. Yeah, and you can work out the momentum of B is going to be equal to, using Pythagoras, the two values that we worked out before, yeah, as being equal to the right angle triangle. 0.0212 was either to the right or forwards, I can't remember, we'll have to have a look up in a minute, and the other value was 0.0133. So if we use Pythagoras and then we can square root it, yeah, you will be able to work out what it was, and you divide by 2 lots of the mass. Remember the mass of each puck, they're identical, is given to us here. Once you do that, Pythagoras, you can work out that the momentum was, was equal to 2.84. It gives you a value of 2.84 times 10 to the minus 3. Okay. Now, 0.039 would be the momentum of A. So this is the momentum of B, this bit, yeah? And this, sorry, the kinetic energy. This will be the kinetic energy because we divided by 2m. So momentum squared divided by 2m will give you the kinetic energy of B after the collision using Pythagoras, and the momentum of A after the collision is from the table. Yes, sorry, it's getting a little bit messy with all the red scribbles. This is from the table. Again, you divide by 2m, and this is momentum of A after. So we've got A and B. You add this value to this value, and you get the total momentum afterwards, A and B together. And this time it gives you a value of 9.75, which is approximately equal to 9 points. So to within, to one significant figures, it is approximately equal. Almost the same kinetic energy. So kinetic energy is conserved, therefore elastic, 99%. Yes, if you work it out. Okay, so I hope that makes sense. We've done 2 more questions, questions 14 and 15, on the conservation laws in particle physics, and then the conservation laws of collisions, which is momentum and kinetic energy, and you have managed to do another video. Thanks for watching. Don't forget to like and share it with your friends if you think it will help them revise, and don't forget, if you haven't subscribed, please do so. Thanks for watching. See you in the next video. Bye for now.